In the second part of amortized analysis, we'll look at the singly linked list. So if you remember the structure of a singly linked list, it looks like this. There is some item I, and there is a successor for each node here. Now we learned that singly linked list is, let us say this is the end. Single linked list is quite good in terms of all the operations, and also if you remember, we used a window to place it on top of a node. So for example, this can be a window on top of this node. Now there was one particular operation that was very expensive for single linked list. That was the previous operation. If you remember, we stored two special references, the first and the last, and well, let us say this is the last for the time being. But all the successor references are for the nodes that are coming next, that are coming, if you like, towards the right side of the list. So if I am right now, my window W is here, it was hard to find the previous. The way we found it was to start from first and iterate through the list. Of course, I'm drawing only a 3-element list here, but in general, the list will be very long. So iterate through the list and always save the pointer of the previous node in some variable. And when you hit the window position, then you get the reference of the previous node in that particular variable. But this was an order n operation, right? Because in general, the window can be anywhere in the list and also perhaps at the very end of the list. Now the question is whether we can do better than this without using, of course, doubly linked lists, because doubly linked lists obviously gives you constant time access to the previous node, because they look somewhat like this. There is a previous pointer and there is a successor pointer, or when I call pointer, I mean reference in the context of Java. But we don't want to use a doubly linked list. The way to use the singly linked list to get the previous relatively cheaply is to do the following. So let us say this is our original list. Again, I'll draw maybe 3 or 4 elements, not more than that, because of my screen space. And this is null. So what I do is, you know that list operations require you to go to different places in the list. Suppose there is a list operation that requires us to go to this one. For simplicity, I can number them 1, 2, 3, and 4. So what I do is, when I'm going forward, I basically reverse this first one remains the same because that is the first reference. First and last, there are 2 special references. So that is okay. But when I'm going from 1 to 2, then what I do is, after reaching at 2, I reverse this reference. That is, instead of a next reference or a successor reference, I make the reference to point to the predecessor or the previous. Similarly, when I go from 2 to 3, then I have this. And I am right now here. And this one remains as before. So what is now happening? Basically, what we have done now is that I can now access the previous node in constant time, because due to this reversal of the pointers or references. So I have now made all the operations constant time. But there is a problem that if I have to now go to the very first one, since or in general, somewhere, let us say this is not the first one, but a node somewhere to the left of the current window position. So this is the window position. then that has become expensive because I have to iterate through nodes and ultimately reach that particular position that I am looking for. So that can be order of n in the worst case, because we don't know, in general, windows will be placed very far away from the node we are looking for. Now, is this the real complexity, that to find an arbitrary node to the left side of the current window position, do we really have to spend order of n time? The answer is no. Again, just like in the multipop case, we have to really look at the context of the operation. So what I mean by context, again, think of a client who has asked you to write a list with functionalities where the client wants very fast access or very fast execution of the previous method. So what you can tell the client is that you can guarantee that if the client is executing the other methods as well as the previous method, in an amortized sense, the cost of the previous method will be order of 1. Why is that? Just like the multipop case, if you look at the situation that you can be at a position that is far away from the start of the list only if you have moved your window over this part of the list, right? Otherwise, you cannot go there. So you have to count that into your analysis. So when you, okay, let us call this method that asks you to position your window on an arbitrary node like this to the left of the current window position as move back. So if you analyze move back n, that is, you have to move back your window n positions, then of course, excuse me, of course you can do that only if you have earlier moved forward those n positions. So what is the cost of moving forward the n positions? N times c. And if I consider the cost of a move back as one cost of 1, then the cost will be n times c again, because I am moving back n positions. And what is the total number of operations I am executing? N operations to go back, go forward from the front of the list to the current window position, and 1 operation for the move back operation, if we consider that operation to be of cost 1. So you can see here we have come to a similar kind of analysis. The total cost is 2nc, and you divide by n plus 1 to figure out what is the average or amortized cost, and you can drop the 1, so it will be 2 times c. So you can see, if you look at the move back operation in the context of the entire picture, that is, you cannot move back unless you have gone forward, then we can do an amortized analysis of the entire situation, and we infer that the total cost is nothing but a constant, or rather the amortized cost is just twice the cost of moving forward or moving backward by 1 position.